Cable guardrails are one of the oldest types of traffic barriers in use today. Some of the first guardrails installed on roadways in the United States used cables mounted on wood posts. Wood posts began to be replaced by concrete posts and cold-rolled steel sections. These in turn were replaced by hot-rolled steel I-sections, the first modern cable guardrail system. This videotape will show the results of recent research efforts to improve the performance and decrease the cost of cable guardrail systems. There are a variety of advantages to using cable systems rather than other types of guardrails. They are easy to install and cost about 1/3 as much as typical strong post W-beam guardrails. The large deflection characteristic of cable guardrails can be advantageous where there is adequate area behind the guardrail. Large deflections cause the impact to be softer and therefore less harmful to occupants. Cable systems can be more aesthetically pleasing than typical W-beam or Tri-beam guardrails, since they do not obstruct the view. The slender cross-section is also an advantage in snowy regions of the country. W and Tri-beam guardrails can act like snow fences, causing a large pile of snow and ice to accumulate along the barrier. The accumulation from wind-blown snow or snow plowing can prevent the barrier from performing correctly and can also cause snow to drift onto the highway. Cable systems offer very little resistance, so most wind-blown and plowed snow will pass through the cables without accumulating. Low installation and maintenance costs. Reduced impact severity. Open profile and resistance to snow drifting are characteristics that can make cable guardrails an attractive alternative in many situations. Although there are a variety of cable guardrail systems in use today, they all share a number of similar characteristics. The AASHTO Roadside Design Guide designates the most common cable system as the G1 guardrail. It was developed by the New York Department of Transportation in the early 1960s. When correctly used in appropriate sites, the G1 guardrail has proven to be a very forgiving barrier system. The G1 consists of 3 cables: J-bolts for attaching the cables to the S3 by 5.7 steel posts, a concrete anchor and hardware for attaching the cables to the anchor block. In recent years, several variations of the basic G1 guardrail have been developed that reduce the cost and enhance the performance of cable guardrails. The state of South Dakota has developed a cable guardrail that is similar to the G1 system, except that a smaller, less expensive post is used. The flanged channel post used in the South Dakota system weighs only 4 pounds per foot, 40% lighter than the standard S3 by 5.7 post. A flanged channel post and soil plate made of re-rolled rail steel would cost about half as much as the standard G1 post and soil plate. The South Dakota cable system cost almost $1 per linear foot less than the G1 guardrail. In this test of the South Dakota system, the cables wrap around the front corner of the small car when it hits the barrier. The cable slips off the post ahead of the collision, and the posts either snap off or bend over as they're struck by the car. The cables redirect the car parallel to the barrier. It comes to a controlled stop after braking. In another test, this large car travels about 12 feet past the barrier line before being redirected parallel to the guardrail. The performance of this system is similar to the G1 cable guardrail system. The location of the guardrail on slopes is an important design consideration. If the guardrail is located on the slope but too close to the edge of the pavement, the cables may contact the vehicle below the front bumper, allowing the car to ride over the cables and penetrate the barrier. If the guardrail is placed at least 18 feet away from the pavement, the vehicle has more time to stabilize before it strikes the cables. In this test, the vehicle suspension had returned to its normal position when the car struck the cables. The cables wrapped around the car just above the front bumper, allowing the guardrail to redirect the vehicle. This cable guardrail transition to a bridge rail is unsafe because it would redirect the vehicle into the rigid end of the bridge. When two longitudinal barriers with different stiffnesses are joined, there must be a smooth transition to avoid pocketing accidents. A transition between a 3-cable guardrail and a W-beam guardrail was developed to solve this problem. The post spacing of the cable system is reduced near the transition, and the cables are passed over and under the W-beam to a concrete anchor buried behind the W-beam's breakaway cable terminal. The large car strikes the cable system and deflects about 4 feet before it strikes the end of the breakaway cable terminal. The vehicle quickly redirects after striking the W-beam system. Steel is not the only material that can be used for posts. Cable guardrails with wooden posts have been used by some states for decades. Recent tests evaluated a modification of the Minnesota state standard design that uses a 5.5-inch diameter post with a 1.5-inch hole drilled through it 5 inches below the ground. This hole helps to weaken the post in the longitudinal direction, ensuring that it breaks away when hit head-on. The post spacing used is 12 feet 6 inches rather than the 16 feet as is typical for G1 systems. This small car was successfully redirected without exceeding the allowable occupant response values. The system was also strong enough to contain and redirect this large passenger sedan. The maximum barrier deflections were comparable to the standard G1 system in these two tests. As with all types of longitudinal barriers, designing effective end treatments for cable guardrails has been a difficult problem. Vehicles tend to stay in contact with cable guardrails longer than other barrier systems. This is generally desirable, but as posts are weakened to soften the impact, the cable anchor takes more and more of the impact load. If the anchor is too strong, it may not break away if a vehicle strikes it. When an impact occurs near the end of the guardrail, the vehicle can wedge under the sloping anchor cables, causing the vehicle to roll over. When this same problem was recognized for both the standard G1 design and the flange channel post design, the state of New York set out to develop an alternative anchorage. The result is a modified terminal consisting of a concrete anchor, an attachment bracket, and a slip base post. The cables pull free from the slots in the bracket during an impact. The whole anchorage assembly is flared back from the roadway to reduce the chance of a direct collision. In this test series, the small car ran over the anchorage in both directions without being tripped. The performance of the improved anchor was much better than the original design. The improved terminal was also strong enough to provide adequate anchor strength in this large car test. Although these collisions are still severe, this anchor design appears to be the only cable terminal that does not cause small cars to roll over when the impact occurs near the end of the guardrail. While cable systems are often used on major highways, their reduced cost makes them particularly appropriate for low-volume, low-speed rural roadways. Even the inexpensive G1 guardrail shown here may not be cost-effective on some low-volume rural roadways. Several new, less costly variations of the cable system were developed in a recent NCHRP project for application on roadways that might not warrant more expensive systems. These new cable guardrails were tested using different speeds, angles, and vehicles than the optional lower service level test recommended in NCHRP Report 230. These systems used 2 rather than 3 cables, with the higher cable mounted 27 inches above the ground. 3 different types of posts were used in the crash tests: the S3 by 5.7 post, the flange channel post, and the round wood post. All 3 systems performed satisfactorily, deflecting between 6 and 8 feet behind the barrier line. The flange channel posts tended to fracture easily, and some were thrown back into the roadway. The cable in the flange channel post system rode over the top of the vehicle, so its performance was considered acceptable, though not desirable. Information on these cable guardrails and warrants for their use have been developed in NCHRP Project 22-5A. These systems could provide a cost-effective guardrail on lower service level highways that would not otherwise be protected. When used at appropriate sites, cable guardrails have significant advantages over other types of guardrails. Low cost, easy maintenance and installation procedures, resistance to snow drifting, and aesthetic appeal make cable guardrails an attractive option for many transportation agencies.